where we're going to be introducing messaging. So if you could fire up any logic, and I'd like you to close out the crown jewel of yesterday, so we start with a blank slate. The crown jewel can be saved for further admiration. Okay, TAs, prepare for deployment. Okay, so do you folks have any logic up? Okay, fair enough. Okay, so it's great to start a morning with the equivalent of the AnyLogic equivalent of 20 push-ups. So you folks are going to guide me now. How do I start a model up? How do I create a model? I want to add a population of persons. How do I do that? Okay, new model. Good. Okay. So file, new model. Good. And we're going to call this simple network, simple SEIR network model. Okay. Great. I'd like you now to go and add a population of people. So this is our model. Here's the main class, the stage in which the agents will strut, and here's the first of our experiments. So I'd like you to add a person class. How do I do that? New agent type. Okay. And we'll create a person. Again, we tend to name these classes that describe agenthood with capitals. Naming is important. Naming communicates effectively. Good naming can help prevent misunderstandings, can help lower confusion, can make a model more transparent. And it's good to adhere to a set of conventions. I'm presenting you one set. You may choose to hew to a different set. The important thing is to gain consistency within your working group as to how you name things. Okay, so here we have a good model, a good start to our model. Could we run this model? Yes. Let's suppose we wanted, but if we ran the model, it would present us with a blank slate. So let's give each of these persons an appearance, okay? And their appearance this time will be a little bit different than before. This time, we're going to give them an appearance that's gathered from the palette and other places. But first, how do we give them an appearance? Where do we go in the model? Is it to main? Is it to the experiment? To person. Okay, so we go to person, open up the person canvas here on the right. Okay, and now down in your palette for many of you will be right behind here, next to projects. I happen to have relocated it here, but you can drag it around to set it at a place of convenience. And we're going to scroll down this palette to this area here. Now, TAs, I see you're standing ready. That's great. And we're going to scroll down to go to this area. It says Pictures. And we're going to use this picture of a person here. And I know from my various boot camps held around the world that people have mischievous tendencies. And some people may wish to use other items from the palette, and I won't protest. Just be aware that if you do, there may be slight differences in how things are done, but we'll try to bear with that. We had one model in which doctors were depicted as fighter jets and moved around in a quite menacing way and interacted with patients. It was less patient-centric than was first articulated 12 years ago. Okay, so here we've dragged in a representation of a person. And thanks very much, Bahrain. That's great. We've given that person an appearance. Ladies and gentlemen, we're about on push-up 3. Okay, what do we have to do to create a population of these people? By the way, notice this is actually an important point that bears note. I've added this presentation before adding the population. Please make note of that. I've added their visual representation before adding the population. That's not an accident. This version of AnyLogic has an issue that if you create the population before adding the visual representation, it's hard to change it later, and you want to be careful about that. Give them some representation before, so that when you add the population, it's lent to representation itself, and you won't be in trouble. You can evolve this presentation later, but just be sure to have some presentation. Okay, so ladies and gentlemen, how do I create a population of these people? Okay, great. So we double-click to main, go on to main, and again, be very careful what we're looking at now. So now we're looking at main, and we wish to drag person to it, okay? And we're going to call this population. That's not privileged in any way. You could call it pop. You could call it people. I like to call it population because I think it's evocative, but you could change the name with it. Okay, so, sorry? No. Mischievous young people may do that. But this is going to be an initial number of agents, 250. And ladies and gentlemen, if I were to run this model now, what would we expect to see? Yeah, so we'd expect to see people. So maybe one of the TAs, if it's okay, you might want to help Law Coach. She couldn't make it yesterday due to reasons outside her control, so if you can make sure that would be excellent. That would be good. So if we ran this, would we see a population? Would there be a population logically? There is 250 person population here. We can go down and we can go count them. But they're all. Why are they all sitting up here? We haven't laid them out, folks. How do we lay them out in space randomly? Today we're going to be using it not only to pick visually where they are, but logically where they are. How did we do that yesterday? We're going to care about logically where they are. How did we do that yesterday? Can anyone tell me? Okay, up in Maine. And what did we do in Maine? We went to environment. Very good. So Dale's on top of it for sure. So go down to layout type and set the layout type to be random. So how did we do that? We clicked on Main. We went down just in its properties and we went to this environment for other agents, and we went to layout type and set it to be random. Ladies and gentlemen, could you run this model? Sure. The properties, you click on it, and there's this properties window down at the bottom. That will probably be at your bottom. Okay, so let's run this. And you should see something like this. Do you see that? Something similar? Okay, good. Okay, we're cooking with gas. Great. So I'd like now to do something that we haven't yet done before. And this, too, is going to be a standard procedure. This is going to be one of your repertoire of frequently accessed steps. And so I'd like you to pay attention. It's conceptually simple, but it involves 2 or 3 steps that are each required to see it with clarity. Okay, step 1, we're going to add a network to this population, okay? And in order to add the network, we're going to do 2 things. Number 1, we're going to go and specify that there is a network and specify, secondly, its properties. And then in the 3rd step, we're going to tell it to make that network visible, okay? Does that make sense? So TA, sector 2. Okay. Okay. So we're going to go add this person, add a network into this model. So ladies and gentlemen, a network between people is a construct that involves a whole set of people. It's not something about one person, just like a traffic jam is not about one person. It's a feature of sort of the whole set. And so it's going to be defined in main the network that we want it to use for people, and it will wire them up accordingly, okay? So ladies and gentlemen, if you go to main and you go to that same area where we set the random layout type, you'll find just beneath that an area where it says network type, and we will ask it to create a distance-based network, okay? That's this network type here. Make it distance-based. And we're going to set it, and this is the second step, to a connection range of 75. Now, you'll notice in here, and later we'll elaborate on them, that there's a variety of types of built-in networks supplied by anyone. These are in no way exhaustive. You can use a user-defined network and have a very customized network. And later we'll be seeing networks that evolve over time. Networks, for example, associated with families or associated with an open population. Other models to which I provided you in part of my example models have affinitive networks. Network where there's preferential mixing. People with similar characteristics are more likely to be connected. But these are a set of built-in networks that are quite useful for sort of examining as standard network types to impose, perhaps to do network sensitivity analysis. So I'd like you to choose a distance-based network with a connection range of 75. Okay?
What's a distance-based?
So thank you. I'm going to describe that. So these networks have different definitions and properties. And I'll be going through them systematically later, but a distance-based network is a network where if you take person A and person B, those two people will be connected if and only if they lie within a certain distance of one another. Okay? It's a spatial proximity. So here 75 is a distance measured in terms of these little squares here. Each little square is 10 units. It's 10, as we say, pixels. This entire area is 50 pixels, so this will be reaching about this far. Any two people scattered around the screen will be connected if they lie within about this range of each other. Does that make sense? Yeah. So you can imagine it capturing distances associated with perhaps its transmission of imitative behavior. So if two chimps see each other, one is likely to influence the other, two people, or or perhaps it's the distance over which birds communicate, or perhaps it's the distance by which a pathogen can spread through airborne transmission. So here we're going to be connecting any two people together, person A, person B, if they lie within 75 units of each other. Does that make sense? Okay. So ladies and gentlemen, that's the first two steps. There's going to be one remaining step. Okay. Question? Yeah.
It's only two though. So we're assuming that there's not a I or. How are those issues?
So it's dyadic ties. So in other words.
But they're moving randomly, so they're instantaneous or.
I see. So right now we won't have movement. We'll see movement this afternoon, and we'll see how networks are captured there. And we'll see how they can be broken and formed by proximity. But in this type of network, we're going to just, for this particular example, it's going to be static. But it is possible to capture them. In fact, that little model I used yesterday to kind of walk through the basic elements of the analogic vocabulary, people were moving close to each other and network ties were formed when they were close to each other. And then when they grew more distant, those ties were broken. And it's readily done in any logic. It requires a wee bit of mechanism that's visible in that other model, and we'll be seeing that, if not this afternoon, by tomorrow morning. Okay? So at any one time, if they lie within 75 units of each other, there'll be a connection, otherwise not. And the basic deal is we have to tell it, hey, go recompute whether people are within 75 units periodically for that case of movement. Okay? Other questions about this? So we've just imposed a network structure. And Maybe what I'll do, I'm just thinking here, and this is a slight variant on it, but I think we'll do it. I'd like to communicate that there is a network right now, okay? There is a network, and I'd like you to build a little bit of muscles associated with a bit of the formal coding that's going on. So I'd like you to open up person, and I'd like you to click on that little shape here, okay? And we're going to go, so double click on person so you see person. That's very important to pay attention to what's open. Click on that shape, and then I'd like you to scroll down, and you'll notice there's this area that says scale X, scale Y, scale Z, right? Okay, I'd like you to type something in there. This is going to be something you haven't typed before, but we're going to use again several times. I'm going to type this.get connections number like that, okay? And it's going to be, I'm gonna put it up here. What does that mean? Oh man. Okay, it means this is referring to myself. I'm going to ask myself, how many connections do I have in space? How many connections do I have? Later we'll see that you can have multiple networks per person, and this is just asking with respect to the default network, how many connections do I have? The one that's going to be built by that network. How many connections do I have? And I want to put the same thing in X, Y, and Z. Okay, so here we go. We're going to put it X, Y, Z, just like that. Okay, this dot get connections number. So we're going to make the person's size depend on how many connections they have. If they have more connections, okay. TA deployment.
Just a question.
Yes.
Sometimes at the end of these expressions we have semicolons, sometimes we do not.
Yeah.
Could you explain?
Okay, so sometimes at the end of snippets we have semicolons, sometimes we don't.
Yeah.
For an expression, something that's designed to calculate a value,
Yeah.
the equivalent of a formula in Excel, which is, this is like a formula in Excel, saying get my connections number, and that becomes 4, or it becomes 1, or 0, right? For that, you never have a semicolon. You don't need it. Where you need a semicolon is where you have what's called, it's conceptually a command. It's called a statement, and it tells it, do this, like assign this to color, okay? The goal of that is not to return a value. The goal of that assignment is to change something, to perform some action, and that's where you need semicolons, okay? And so yesterday we had these snippets of code where we said color equals red. Remember when someone was in an effective state? Color equals red. That's telling it to do something. It's not calculating a value. It's not returning 3 or something like that. It's not a formula. It's a command. It's an imperative. Do this, and that's where we need the semicolon. Is that helpful?
Yeah, very.
Okay.
One quick related question. Sorry.
Yeah.
You used this today and self yesterday. When do you use this and when do you use self?
Almost always you use this to refer to the current person.
Okay.
The one confusing exception, there's actually 2 cases, but they're very unusual cases. I have not seen them much. And self is basically used when you're creating a new agent and you wish the features of that agent to have interdependencies. So you wish their income, for example, to be based on their education or based on their sex, like we had yesterday. There, we're creating this new person, and the thing that's confusing is it's happening. You're describing this associated with the population. So this is actually main. It's referring to main. The person is not yet created, and we're telling how we're going to calculate their properties, and so we use self to refer to the person who's created. That's in any logic thing, okay? And there's one other similar case it's obscure. It's not a common thing. Almost always you're using this to refer to the current person. In this case, it's the current person. This is me. I'm saying how big should I make my image? This is the current person. It's me. And the dot basically says, hey, okay, ask myself to get my connections number. We're going to see this a lot more today, those who go to the Java tutorial. Yeah.
I have two things, but I want to follow up on that.
Yeah.
Stated in systems language, would it be for an instantiated agent, use this, or non-instantiated, use self?
For this other case, but this other case is very ad hoc. It's one of two cases I know of in any logic, and I think that description may cover both cases, but yes, I think it covers both cases, but I have to double check.
So
the
you
other
would
one.
just build self for non-instantiated.
Yeah,
So you wouldn't have
yeah. You can basically almost never have it. I very rarely encounter it in my modeling, but I'm trying to show you how you can do certain things that you may want to do, and there on that occasional time you use self. But I'd say by and large you can forget about self except for that case and use this. Okay.
Yes. My real question is why scale Z? What is scale Z, and why are we bothering
It's
about
the
it now?
size. It's how much. So a scale of 1 would be the normal size.
Right.
Scale of 2 would mean twice as large. It will be twice as large as x.
Right.
So it'll be sort of big, and scale 3 would be 3 times as big. So we're going to make it so visually they appear bigger if they have lots of connections.
No, I get that, but scale Z, I'm sorry.
Oh, scale Z. Oh, yeah. Sorry.
Three-dimensional.
I'm sorry. Scale Z. It supports 3-dimensional depictions of certain things. Here we're not going to be using it, so probably we can leave this out and be just happy camper. But I threw that in there just in case there was any need to do so. You can leave it out and see what happens. So can we do a build? Okay, TAs. Sometimes things happen at build. Okay, so do a build and see if there's okay, people need help? Okay, so what we're doing is we just imposed a network, ladies and gentlemen, and we're going and seeing if people are built into the network. That get connections number, that's asking how many people, oh my gosh, look at them, they're a big, I don't know what, it looks like a slime mold or something. Okay, well, some people are really big, but maybe a little bit too big. Okay, let's go down, let's go change that. Let's go change that expression to make them smaller. So go to person, and instead of scale, that scale equals this thing, let's make it this thing divided by, I don't, really we should be calling do it with a log. Yeah, how to fit 0? So okay, log of 1 plus this connections number. Now, really, we should be calling a function, and if Dylan will be exhibiting uncomfortable behavior, and I'm exhibiting, if not heart palpitations, I'm exhibiting revulsion. I'm glad I didn't eat my full breakfast yet. But really, we should be calling a function that would calculate this. But I don't want to introduce functions yet, and so we'll see how they can clean this sort of stuff up later. So this is 1 plus this connections number. So if they have 0, they'll be of size 0. If they have a large number of connections, this will be maybe 4 times the size that they are, etc. Okay, so here we're setting their size visually because they're too big right now, and it puts them disproportionately big very quickly, even if they have a few connections. So I'm saying log of this thing. Here we're basically stating how big should that image be of them, and here we have people of different sizes. People who have more connections tend to be larger. This crowded area, people with few connections tend to be smaller. And I'm right-clicking on this to move it around. You can kind of right-click. So here we have people of different sizes based on their connections. So they're connected in a network, ladies and gentlemen. They're actually built into a network. Okay, TA help. Okay? They're built in a network. So who needs more time just looking at that code here? Who would like me to put it up on the big screen? Okay? Okay, there we go. So they have connections. Does people want this up on the screen more? Yes or no? Are people ready to go on? Are people ready to go forward?
There was a problem earlier.
Oh, okay. Okay. Okay, thank you. Folks, by the way, I forgot to note, there's power bars in the front of all these stations here, and the IT staff were hoping that we could ask people to plug in to the power bars in the front of these machines if you have a laptop, rather than unplugging the actual machines, because unplugging the machines can cause problems for the next person to use it, among other things. So in any case, there are power bars in the front if you need to reach them. Okay, who would like more time with us on the screen? Yeah? More time? Okay, are we ready to go forward? So ladies and gentlemen, what we need to do now is we need to make it so that the network displays. People are wired with different numbers of connections, hence they're different sizes, right? This is saying if someone has more connections, they'll be bigger. They have more connections, as judged by this, they'll be bigger. And along the X, Y, and Z axis. We're not really using Z. We're not using the three-dimensional abilities. But let's actually show those connections, okay?
So we were not using it, why did we still put it in there?
You don't have to. We could. Here, you want to? Let's see if we could strip it out. I bet we can. 98% certain you could strip it out without adverse effect. There we go. Yeah, strip it out. Strip it out, and that looks less horrendous to me as well. I'll take a few more bites at breakfast. What's that?
What did you strip out?
I stripped out the Z. There was a question, do we really need the Z component? Sorry, Z. So I stripped out this one. They said, do we really need that? And I said, no, 98% certain. And I was, my wager was rewarded. Okay, okay, now I only have a little bit of grossness, so I'll eat a bit more pancake. Okay, so moving right along, let's now have people's connections show. People are connected to each other. They're bigger if they have more connections. Do they not? Let us now wire them up. Let us see those connections. So ladies and gentlemen, this is the third key step. This whole step of making people appear different sizes, that was a sideshow. The first thing we did, in main, we set it to impose a network. Second thing we did, we set that network to have properties of connecting people if they were, say, within 75 time units. Later we'll see other possible properties. This final thing, we're going to get them to appear visually. And for those who are from AnyLogic 6 background, pay attention. This is new. I have a whole sheet that I've uploaded to you on the Google Drive docs, which systematically goes through differences. AnyLogic 6 and 7, you may want to take a look at it. This is one of the differences, and it's one of the most practical day-to-day differences. Ladies and gentlemen, go to connections here within person. So open up person and go to connections. This connections manages the visual properties of their connections as well as, ladies and gentlemen, their logical properties. So you'll notice here, for example, that you can have bidirectional links or unidirectional links now. You can set their visual properties by down here at the bottom where it says animation. So I opened up person, I clicked on connections, and I'd like to draw a line connecting agents. And I'd like to draw it behind agents. You could just leave it like that. Draw a line connecting agents here. Okay? Do you see that? Are people okay with that? So in person, I opened it up, clicked on connections, scrolled down, and notice we could further say the properties of this line, whether we want it to be thicker or thinner. AnyLogic has very nicely incorporated this ability to specify properties of connections, not making it all reduced to agents, but allowing us to specify characteristics of these things that link agents. Okay, so ladies and gentlemen, having done that, having checked this box, so
Just a question again. Given that we are describing the connections for the whole population, why are we not doing this on main?
this is an attribute. It's a very good question. The idea here is that each person has connections to others, and we're asking it to sort of set for its dyadic connection. So this is a given agent. Well, here we're describing in person sort of the theory of a given agent, and we're saying any connections that it has, we want them to draw lines to other agents. Does that help?
Yeah.
Yes.
Why is connections on the canvas instead of being on the palette where you would just bring it into onto the canvas?
Because by default, everyone has one set of connections, but you can add additional ones from the palette. So if you go over here to the palette and you scroll up to the top, you'll actually find that there are a set of connections that you can add in. So these are the default connections, but a given person, as we know, a given person can be enmeshed in several networks. I have a family network. I also have a network of coworkers, and there may be networks associated with other sorts of activities. So, for example, in a model for transmission of HIV, we might have a sexual connection network and a needle sharing network. Both are routes for transmission of HIV, and we can describe those using not only these default links, but we could have other types of links, each of which will be a distinct type of network, having you connected with different people. And so this is just a default set of connections that are there for it to be wired up into these pre-specified networks, but we can specify other networks to which we're a member. Does that help?
Yeah, it does. It doesn't seem very logical to me, but it did help.
Yeah, they have, as a fellow software developer, have some sympathy. Among other things, they didn't want it, because if they didn't have a default network type, and you said, wire these people up, it was like, I don't know what network to wire them into, and so they wanted to be backwards compatible easily with AnyLogic 6, to have more or less seamless import of AnyLogic 6 models. And I think the way they did this was to say, okay, by default, people have a default set of connections, and then we can allow people electively to add in other types of connections for other sorts of interactions that are not wired up automatically, but where you instead manually wire them up. And you can find an example model given you where we have agents in multiple types of networks. Yeah.
I think a minor note, but at the top of the connections, sort of under the properties.
Yeah.
In the properties, but above the animation, it says you can show the name and you make it visible, but that's not the actual network. That's just the icon for it.
This is just the icon. So this.
If you said don't make it visible, you could still draw the network.
Yes.
Okay.
Yeah. So the deal is that this little thing that says connections is by default visible, but if you set not visible, it'll make this connections thing not visible when we're running the model. We can make this thing invisible, but it's this box down here that dictates whether or not the connections between people are visible. Is that helpful? Yeah. Okay, so let's go run this. So we should have something like this. So now we see that people are knit into these networks, and individuals with fewer connections are, as we indicated, smaller. Individuals with a greater number of connections are larger. So this is a very dense area of the network over here. On the left, this is a less dense region here, over here, etc. So here we have people scattered around the space. They have different numbers of connections induced by proximity, and they're correspondingly sized. Okay.
Why does it still say not?
Oh, that's because, very good question. So another choice made here was to make every construct like main and agent classes in AnyLogic, they're agents. Okay, so main is an agent class. You could actually have multiple mains interacting over a network. They seem Sorry, my brain just used. Indeed, this is strange, but think of it instead as like you get multiple cities in a distance-based network. The cities are connected with one another, so Ottawa connected with Gatineau, and there's a network connection between cities. And so as a general rule, whenever you add in a new one of these, there's a connections always. And so Maine has a connections. I actually don't think it will be that meaningful to have multiple mains, but I'm thinking multiple, and think about a multi-level model where you have cities and neighborhoods and people, and you have neighborhoods, a network of neighborhoods meaning proximity to each other. You have a network of cities, which might be a distance-based network based on road connections or rail connections or flights or what have you. And then you have people. And so Maine has a connections, but I've never used it. It's just there as a kind of, because it's just another one of these types of things. But you've got to watch out, because sometimes you can think you're in person, you're actually in Maine, and you say, oh, I'll go modify the connections. And it's not going to be meaningful.
So this one is the one from Maine.
This is the Maine, this is connections of Maine. And if we want to avoid being confused by that, just like we said, you could go up to Maine. Let's go down Maine. And then let's click on connections, and let's make it not visible. Right? And now when we run this model, we will not see it here. Right? Is that helpful? Yeah.
You could also go down into person and see the connection to a person.
Yes. Thank you. So let's run the model again. Thanks very much. Beautiful idea. So let's go down to the person. Oh, that was an AnyLogic 6 thing, but these are the connections. Yes, this links it, but it doesn't show them visually. It doesn't show to what they're connected, but it shows, okay, this person is connected with other person number 4 in the population, 12 in the population, 32, 33. This is person 7. They're connected with number 3 in the population, number 39, 74, etc. And so these are the connections that with which they're associated. You notice they're of different sizes correspondingly. So let's find someone really smaller. And here's a nice smaller person, and they have fewer connections. Okay? Does that make sense? People are connected now. Okay? Good. So we just introduced networks and so on. So, ladies and gentlemen, I'd like to now to build on those muscles we developed yesterday, and I'd like to go and elaborate this model with features having to do with state charts and messages. So we're going to introduce this notion of a message by which people can interact, because we still have solitudes, but we've laid the groundwork. We've put in place the mechanisms by which they can interact with others through this network. Okay? We've lent them context. We've situated the agents, and now we will enjoy the fruits of those connections. Okay. So I'd like you to go to person, and I'd like you to add a state chart. And these are a little bit more push-ups. How do I add a state chart into person? Tell me where to go.
State chart in thing.
Okay? Yeah, I go to the palette, and where do I look in the palette? I look in the state chart area. State chart, down here in the palette. Notice I want to describe the evolution of a person, so I go to person. Very important thing. Okay. This is found in person. This is a thing about a person. Good. So we're going to capture a model very similar to what we first saw yesterday, but build our own here. We're going to divide them into 3 categories. We're going to divide them into susceptible, infected, and recovered. Okay. So here's a state chart, and we're going to call it infection state chart. Okay. Sometimes it's useful to give that name of a state chart so that you know that it is what sort of thing it is if you see it in a list. You know, oh, that's just the state chart, and that allows you to sort of ask it for questions and so on later. Oh, instead of calling it just infection, which might denote the transition, calling it a state chart is kind of connoting the fact that it's this broader construct. Okay, I want to add a susceptible state, an infective state, and a recovered state. For those who do infectious disease, do you want to see an exposed state, a latent state? Do you want to have that? Okay, sure, we'll have that. Okay, great. So, ladies and gentlemen, I'd like you to tell me how to add these states. Okay, drag them in. Okay. Okay, so this will be susceptible. Okay. There we go. And then we're going to drag in, shall we call it latent? It's often commonly called exposed, but let's call it latent. Let's do infective, and let's do recovered. Now, ladies and gentlemen, we're talking a lot, given the interest of the audience, we're dealing a lot here with communicable illness, but it bears note, for those who work more on the population health side, with respect to social determinants of health for non-communicable diseases, it bears note that a lot of these categories, and this notion of contagion and transmission through networks, that carries over to factors directly relevant to chronic disease. I probably don't have to tell this audience, but you know, if we think about chronic diseases that are obesity-related, for example, and we think about risk factors for obesity, there's issues concerning imitative behavior, transmission of knowledge, attitude, and beliefs, concerning physical activity and nutrition. There's a variety of types of influence that spread via networks of other sorts. And so while we may be describing it in our terminology and informally as kind of a matter of communicable disease, the scope and the significance of this modeling extend outside of that. Okay, so ladies and gentlemen, how do I connect these up? What do I use? Okay, transitions. Good. So we're going to have a transition here. The very first one is going to be called infection. And right now we're not going to make it, we're going to make it deterministic, that they're automatically infected. And this will simplify things. Later we'll see how we can make it conditional, contingent, how we can make it probabilistic. We're going to make it this sort of transition from susceptible to latent, and we're going to set it to be a rate transition for now. Later we're going to come back and we'll set it to be what's called a message transition. Okay? Okay, and then I'd like you to have from latent to infective, I'd like you to put in a transition here, and this will set without wanting to spend too much time on the decision. I think I'll say emerging from latency or becoming infectious, becoming infective, something like that, infectious maybe. And we're going to set this to be a timeout, which will occur after 3 days. We're going to have to remember to set the time units in this model in just a minute. 3 days, timeout, and then finally from infective to recovered, I want to set it so that here we go from infective to recovered in a mean time of 10 days. But I want to do it with a rate transition. So this will become, we'll call it recovering. Now, it's good practice to show the name, and I believe that that's what allows it to also be allowed to sort of show visually when it's going to occur. We want it to set a rate transition. And ladies and gentlemen, a rate transition specifies a chance per unit time going from this to this. Let's suppose our unit time at days. What value do we need if we want the mean time spent, the mean residence time, the mean time spent in the infective state to be 10 days? How long, what's our rate have to be? What's our chance per day have to be to make it a mean of 10 days in that infective state? 0.1. 0.1. We know that in other areas from those from system dynamics background will recognize that if you want a mean time in a stock of 10 days, the chance per unit time of a given person going across the flow downstream should be 0.1. 1 over the mean time, okay? So let's make it visible up here for each of these names, okay? Show name, okay? Becoming infectious, and then this top one will show name here, call it infection, okay? That's great, ladies and gentlemen. Let's suppose that we want to lend this color. How can we do that? How do we lend it color? Okay, we can put in a variable, that's right. Okay, so let's put in a variable. So let's go add in a variable, and we do so through the top one of these, and we're going to add in a variable. We'll call it color. Okay. Now, what will the type of this variable be? It'll hold a specific color, but it'll be the type associated with it. It'll be, when we talk about type, we say sort of what's the set of all possible values that this could hold. It's not a double, it's not an integer, it's not a true or false thing. It's a what? It's a color with a capital C. That denotes sort of its set of all possible colors, a sort of notion of colorness. So we say other, and we say color here. Okay. Okay. Good enough. Now, how are we going to set the color, ladies and gentlemen? Who needs help here? TAs, stand ready. Okay, TAs, sit ready. Oh, okay, one's standing. Okay, ladies and gentlemen, how are we going to set the color? Let's set it to be green and susceptible. Latent will be yellow, infective red, and recovered will be gray. How do we do that? Okay, good. So click on susceptible. I'd like to lend additional significance to my words from yesterday, if I may be so presumptuous. So yesterday, when we wanted to change the color, we did so in this thing called entry action. So what that entry action means is when someone enters that state, you want something to happen. You want it to do something. You want to tell it as a command, do this. And what we're going to ask it to do will be to set that color variable to a color indicating the characteristic of the state. Okay? So let's set this color variable for susceptible to be green. I like to put it in all caps because I find it more notable, stands out a little bit. But you may want to put it in all lowercase alternatively. And I like sort of visually setting this color to indicate it, but that doesn't automatically change the color. It visually while it runs. It's just the depiction here. It doesn't make them appear different colors. Okay.
But does that then later serve as kind of a legend?
Yeah. Do that? Exactly. It's kind of a legend for what these colors mean, and that's significant. Yeah. All right.
Under the variable, you put the type as color with a capital C. Does that matter?
It does. The capital C, we use capitals to denote whole categories of things or classes of things. So like person with a capital P, that's not just a particular person, it's personhood. It's sort of, again, the theory of person. If we had bats, we might have a bat class, and it would be a capital B indicating a sort of the batness that's being described there. And similarly, color with a capital C is sort of colorness. It's a set of all possible colors.
And lowercase c would be just
a particular color, a specific color. So it is like if we called a particular person, we'd use a lowercase p. Okay. Okay, ladies and gentlemen. so we have that. We have it green. Let's go set this one. And tell me what to type, folks. You tell me. Color equals yellow, okay? Okay, we're up to about push up 20 here, okay? And then similarly for infective, we're gonna make it color equals red, okay? Color equal red. And finally for recovered, color equals gray, okay? Color equal gray. And notice it's AY, not EY. Okay.
On the infection rate, we just left that at 1?
Right now we left it at 1
Okay.
for didactics. We're going to change that in just a minute. All right? And it's a rate.
Right.
Set it to be a rate, yeah, of 1. Okay. Okay, ladies and gentlemen, what's the final thing we have to do? Currently, this model is full of sound and fury, and it's signifying nothing. Yeah, we have to make their appearance somehow be tied in with the variable. And there's the rub in this case. So let's go check that out. So right now, and this is one of the motivations for choosing different shapes yesterday, we're going to go look at that person, and we want to go set their color. We go look down in their properties, and okay, there's their rotation and their XYZ and their scale, but there's no obvious color there. And ladies and gentlemen, if you want to do this with this sort of orientation, you can do so, but you got to go over here. It's a little bit more involved. You have to go beneath person to description of their actual shape, and here you can set their color. Okay, here you can set the color as you see fit. There's a fill color. So this is a little bit confusing in AnyLogic, and to be honest, I don't totally grok why for some of these shapes you have to do this, but I think it's a shape that's composite. It's composed of, in general, multiple pieces. In this case, it only lists one piece, so I'm puzzled by why it was a problem here. But it's over in this projects area. You have to expand presentation, expand person, expand shape body. And ladies and gentlemen, let's set both the line color and the fill color to be given by color. Okay? Color, and then the fill color will be color. Okay? Okay, who needs help here? Okay. Okay. Okay, folks. Who needs me to pause and explain something? So I'm trying to build up actual concrete familiarity with AnyLogic mechanisms, and this is one of the warts I wanted you to see. That sometimes you have to go, if you have these more complex shapes, which are neat and there's lots of them, sometimes be aware that to set that color, you have to kind of expand them on the left-hand side here. Were it not so, but right now it is, and it's not too big a problem as long as you know where to go. Okay? You might be offset by, hey, why does it not have a color? Okay. Okay, great. So TAs, I need you to spring into action. So if you could check out Vikram's errors there. Okay. Who else needs help? Okay, help in the back. Okay. Who else needs help? Okay. Help. Okay. Front deployment. Okay. Okay. Additional TA forces stand ready. Okay. Anyone else? Okay. Are people ready to move forward?
No, not really.
Okay. Okay. Okay, yes, okay, TA, frontal deployment. TA,
No,
TA?
no, I'm fine.
Oh, you're fine,
No, I'm
okay.
just amazing with the colors. You know, if I had some LSD, it could be, wow.
Okay, okay. If this demand keeps up, maybe the TA should form a phalanx that marches around the room. And, okay, okay, so let's, if we go run it, we should see something along these lines, right? Okay, so what did we just do? Big picture, we didn't do anything that too different from yesterday. We added in a state chart. We're trying to exercise those muscles developed from yesterday. We want to revisit basic actions that are practical actions you'll need most days while building AnyLogic, using AnyLogic. You need a lot of the days, and these are a few of them, so I'm trying to rehearse them, revisit them, recap them in a fuguish sort of fashion. And here we added a state chart. We added a variable. The variable is color. It's an instance of, a particular example of, it's a reference to a particular color, drawn from color with a capital C, which depicts sort of set of all colors and their properties. We then, for each of these states, set the color to a certain value. We set it to be green here, yellow here, red ineffective. And then finally, we set over here for the person's presentation. We found that with this particular type of depiction, we needed to go over here on the left-hand side and set this internal property rather than the person as a whole. That's a bit confusing. I wish it weren't so, but as a practical skill, it's important to know how to do that. You set it here, the shape body, to have the characteristics of color. So this is kind of recapping yesterday, but building those muscles. Are people okay with that? Yeah. Okay. So now we're going to take a step where we as a group have never gone before. Okay? Because we still have people as solitudes. Colorful solitudes, yes. So if we run the model, we should see something that visually is somewhat striking. But now let us have these people interact. So in order to interact, we're going to do two things. Two main things, and then one final coda, one final denouement. So the first thing we're going to do over here, ladies and gentlemen, is we're going to introduce a mechanism known as a message. And a message gets sent from one agent to another, either a neighbor in space or a neighbor in a network, or perhaps just to a random person in the population. We can send messages. These messages send information. They communicate. They're communicational means. And don't get distracted by it being a message. They're ways of interacting. They're ways of one person nudging another, or interacting with another in a discrete sort of way, in a direct way, with a discrete action. So ladies and gentlemen, go up to infection here, and I'd like you to set it so that it's a message transition. And now we'll see something that we have not seen before. We'll see a transition with this kind of little envelope in it. It indicates this is triggered by receipt of a message. Okay? Now, when we do so, we can actually be very particular about the type of message. So if you had a model that was simulating spread of hep C and HIV, you might distinguish between an HIV-related infection message and a hep C, one is handled by one state chart, one by another. Here we're just going to say, whenever we get any sort of message, we're going to go do this, because there's only going to be one sort in our model. But in general, you'd say, if it's a particular message, do such and such. Okay? People comfortable with that idea? So when they get a message, they are going to react. Now, that's one piece. So they're going to get infected. They're going to go, if this is important, if they are in the susceptible state, they will then proceed to the latent state. If they're already latently infected or they're already recovered and they get that message, they're going to ignore it. It's not going to do anything significant. It's only if they're in this state they're going to proceed by this infection. They're in exactly one of these states at a given time, and with respect to this state chart, and if they're in the susceptible state and they get a message, they'll react by becoming latently infected. If they're in another state and get a message, it won't make a difference because there's no message transitions out of that. Okay? People comfortable with that idea? Okay. In general, you can have multiple transitions that handle messages within a state chart. So if you're in one state or another state and you get a message, you could do something. Maybe in the susceptible state it infects you, otherwise it boosts your immunity or something like that. You could readily do that. Here we just have a single message transition. So this is half the equation, half the major equation. What, ladies and gentlemen, is the other piece of the puzzle? Sending a message. Who's going to send this message? It's kind of this disembodied message that zaps people right now, but it has to, from whence will it come? We know whither it goes, but from whence will it come? So let's go up to our properties, and let's go down here to state chart, and we're going to draw in a transition that will be sending messages. Now I'm going to do something which may shock you. I'm going to do something which may distress potentially you.
That scares us.
Sorry, that was too histrionic. Hopefully not, though.
Are you sure you got enough sleep?
Yes, but lingering effects of the previous night wear on. Okay, so we're going to draw an internal transition. And this transition is going to be occurring within a state. So as long as they're in an infected state, they will periodically, things will happen to them. That won't take them, it won't remove them from the state altogether. They're going to remain in the state. They're not going to go to another state. Let's put it that way. But it's going to trigger. It's going to trigger some action. So we're going to set it here with so that within the state at a certain rate, and the rate will be 10 contacts per unit time. They're going to actually send a message. I'm going to actually lower that down so let's see. Yeah, so no, it will be 10 contacts per unit time here, okay? 10 contacts per unit time while they're in this state, and here, so it'll be a rate of 10 per unit time, and for each such contact, they're going to send messages to their neighbors. Boy, is that awful fast. I'm worried that that's going to be too fast for us, but we'll give it a try. Now, this is going to be the key step. We're going to be sending a message to our neighbor. So we're going to ask ourselves to send to, and you can send to random connected. This is this choice here, send to random connected. How am I doing this? So I called it up by doing Control Space, and I use the keys to go down to that, and then I press Enter. And I say send to random connected infected. Control Space, yeah.
Where do you put before this or after?
I'm sorry?
Where do you put the cursor?
Oh, so I did this sort of thing here. I'll do it again. So I start typing send to Control Space, and then it proposes these, and then I use the up and down arrow keys to select the one I want, and then I press Enter, and it will fill it out. So let me do that again. This is a key skill. Send to Control Space, and then I move it down, and with the arrow keys, and I press Enter. And I'm going to send the message infected, or infect, okay? Infect. The actual message is immaterial here because there's only one type. If it receives any message, it will be fine. But in general, you're going to want to be very consistent. If you test that message at the point of becoming infected, then it needs to be exactly the same. Here, I'm putting an exclamation point just by convention. I like to indicate that it's a sort of imperative. Okay.
So, I'm not sure. Well, you said you're putting an exclamation point, why?
Just to connote the fact that it's an imperative. We're telling this other person to do something.
Okay.
But it's not particularly significant. It doesn't care about the exclamation point. It's just a convention I use.
It does care about the quotation.
The quotations are actually, this indicates what's to be sent in the message. What's the content of the message? We could send information. We could send who infected them, ourselves infected them. So we could have it record who infected them. And actually, we don't need to do that to know who infected us. There's other ways to extract that information. We might send message that tells us, tells them the location where we're currently at in geographical coordinates. We might send them a message that says something about the size of the infecting dose that we're providing them. Here we happen to send a message that says the nature of the action that we're seeking with MSA.
You're sending is to transition between susceptible and latent.
Well, we're sending this to some person to whom we're connected in the network. We're picking a random person with equal probability with whom we're connected in our network, and we're sending them a message that says basically we've contacted them in an infecting way. Okay? And if they're in a latent state, they will become infected.
But you put the message between susceptible and latent.
This is the receipt of the message, so if they're in a latent state, they will become infected. If the person who receives it, so imagine there's me, I'm in a network with several people around me.
But if you look at the diagram,
Yeah.
the message is in the transition between susceptible and latent.
This is the message receipt, so between susceptible and, oh, sorry, it's further up, I'm sorry, I misspoke. I'm used to doing this with an SEIR. It's actually 2 levels. It's up here.
Right. So
Yep.
That's where the message is going.
In another agent. So in other words, Winchell and Raheem, could you come over here? Please come up and accompany me on this stage. Please. Yeah, I want to illustrate. Okay. So these folks are in my network. I'm standing near them. They're near enough to be connected to me. They're within 75 units. So they're connected to me. And I'm currently in the infective state. And, yeah, okay. One of you got to be susceptible, okay? So I'm infected, Raheem's infected. Winchell is susceptible. So I'm connected with both of them. And so I'm in the infective state. And periodically, I'm coughing. And so I'm presenting some infective dose that Winchell is going to, Winchell or Raheem could be exposed to. So at a given time, I have a cough. Raheem is exposed to this cough. Raheem's already infected. Maybe he's in the latent state here. And he's not going to, if the message is not going to make a difference for him. He's already in latent state.
Oh, I see.
And so he's not going to get infected. But then I'm going to cough again or sneeze, and Winchell is going to get exposed. Winchell is susceptible, and therefore Winchell will get infected as a result of that exposure.
Because you don't have a message relating to infected.
Right. Here, Raheem was already latently infected, and so this additional cough that I do is not going to make a material difference for him.
So then the thing is, when you put the equation or the formula in,
Yeah?
why do you put random? Why not too susceptible?
Oh, I see. The idea here is that in a given, it's a great question, and it will depend by context. So the choice of how we simulate this will depend a little bit, actually depends significantly on context. So, for example, let's suppose that they were my lab mates. and I was sitting in a cubicle and they're sitting nearby. Me coughing might expose all of them, okay? In which case, we do send to, I think it's all connected is the name of it. On the other hand, if this was a needle sharing situation where I was sharing needles, okay, this is something. But if it were a needle sharing situation, it's dyadic. I'm sharing it. Well, actually, no, it's not necessarily, is it? But you can imagine a case where there's a sexual interaction. Sorry.
Maybe you guys want to sit down there.
Don't stand too close to me, okay? If there was a sexual connection that's dyadic, then there would be sent to a particular person at a time. But it depends quite a bit on the nature of the of the exposure event, whether you send to all or whether you send to a particular person, and indeed whether you're connecting only with people over a network or whether you send it to anyone in the population.
So what does the rate then denote here? So because when you run that model for like
Yeah.
several times, and it said does not result in anybody, like everybody
Correct.
is acceptable, and nobody
Correct. And there's a reason for this. This means 10, so let's suppose the time unit of this model, we should go set that in a moment here. Suppose it's the time unit is day. This means 10 times a day, on average 10 times a day. It's a Poisson arrival for the, that's a significant statement. There's a certain chance per hour, or per day, chance per unit time. So on average 10 times per day, on average once every 2.4 hours, there's going to be an infectious event of some sort. So this could be a cough, it could be a sneeze, it could be a needle sharing event, whatever the domain is of interest, but it's occurring 10 times a day on average. Sometimes it may occur more than that in the course of a day, sometimes less.
So I mean, how would you do that? Like for a needle sharing side, I can talk today. If you talk about that with viral infections, that's the way that
Indeed. The reason I haven't made it dramatically higher here is because there's automatic infection given exposure. So in other words, one thing we haven't built in at this point for simplicity yet, and we're going to add it in just a minute, is if there's, right now, if someone's exposed, they automatically, the pathogen is on, if a susceptible is exposed to this bug, they're automatically infected right now. Because right now, if they receive that message, they're automatically infected. So if I cough right now and Windchill's susceptible, he will automatically become infected right now. And so you can view it as transmitting an infecting dose. If we want to really capture the effect of coughing, for example, or sneezing, really what we're talking about is a small infection probability per exposure event. And we'll see how to capture that in a few minutes.
The other point sometimes, like with some infectious diseases, your degree of infectiousness.
Indeed.
So with cough or whatever, with some
will change.
So will change over time. So you're in the early stages.
Exactly.
So you may be more infectious, therefore you even if you cough once.
Yeah, that's right.
But later on you probably cough
Right.
or depends on the disease.
Exactly.
But no matter how much you cough,
Right.
you may not actually infect people.
Precisely. So like for HIV, where acute HIV infection involves very high risk of transmission, both because people don't know they have it yet often, and because of the very high viral load levels. Then what you could do is you could actually subdivide the infective state into several states of acute HIV infection, and then chronic or longer term HIV infection, where you have lower viral levels and
So the other thing I suppose we can also subdivide the infection. We can also add another state there because some people are there is an epidemiology difference between infection and disease.
Right.
So you cannot actually manifest it.
That's right. So there's sort of this state associated with latency, and then there's a separate issue of incubation, whether you develop the symptomology. And we could capture that within the state chart or the separate state chart involving evolution of the symptomology. So whether you're asymptomatic or symptomatic, because as you know, for a significant number of diseases of concern, or conditions of concern, say gonorrhea infection often has long-term asymptomatics as well, particularly among women, and they're, you know, you may have a whole state chart associated with symptomology, or you could capture it in this state chart if you wanted to. Okay, so those are good points.
I suppose we're not doing it now.
We're not going to do it now. Later we'll see a model where tomorrow or the next day where we're actually capturing viral levels changing over time in a person, and that may make a material difference in the transmission of it. Okay, good question. Yes.
So just to clarify, by using the send to random rather than send to all,
Right.
we're capturing the fact that you have these connections, but maybe on that day you didn't have the right contact with either your neighbor or your connection
Right.
that would result in transmission. So you're introducing stochastics.
That's right.
Right? Okay.
That's exactly right. So here we're setting it to a randomly chosen neighbor with the idea being that it's not simultaneous with all. But in other cases, we may be more a broadcast situation. Even in the case of co-located workers in cubicles next to each other, or you know, horses in a pen, you know, there's often could be just by chance some of the folks who are commonly associated with them are not around. Some of the animals are not around, and so we might send to a subset, or you know, might not send to all. But sometimes you will send to all if it's proximity you're capturing. If you're capturing people's mobility, and right now there's 3 people around me, I might send it to all of them. So it will vary a lot on a per condition, per situation basis, whether you send to all connected, whether you send to a randomly chosen specific connected, or whether you send to anyone in the whole population. That will depend a lot on the context you're trying to capture. And there is stochastics involved in this, because the vagaries of whether I send it to Winchell, while I happens to still be infected, versus to Raheem, who's already infected, that will make a material difference as to whether Winchell gets infected, right? Okay, good question. Yes.
So if you run it right now, why is everybody staying?
Okay. So that's the mystery I want to put to the group. There's one critical missing piece.
Well, just one question before that. What happens if you get hit by a message from a number of agents, persons at the same time? So just pick one of them?
Right. That's a good question. Yeah, it's whichever one was sent. About this a little bit.
Yeah.
It will pick. So you can set it in any logic. So the question was, if you were hit by several messages at precisely the same time, time here is actually set to be continuous. So it's very, very, very unlikely that someone will hit you at precisely the same time. It would take an extraordinary coincidence for someone just like it would in the external world, for 2 people to cough right next to you at precisely the same time. If it happens, you'll notice in an experiment you can set it. How do you handle simultaneous events? Do you have it choose randomly which one is scheduled, or is it just based on sort of which one happened to send it first in terms of the execution of the model? You can tell it to handle this different ways. Is that helpful?
Yeah, that's great.
Oh, okay, so folks, let's run this model here, and why is it we don't see anyone get infected? You don't have anyone starting infected. So that's the final piece, ladies and gentlemen. And this brings up another key piece in learning. How are we going to start someone to start that index infective? So ladies and gentlemen, there's several ways to do this. I'm going to show you a way that I feel is particularly transparent, which is a strong desiderata in my model, having mechanisms that are clear to someone looking through the model. And this mechanism will involve our first use, where we introduce what's called an event. So if you go up to main, you go down main, and you go here within the general properties of the palette, you can drag in an event, okay? And let's call this event initial infection. okay? And the initial infection event will go off at time 0, okay? It occurs once. It's a timeout, occurs once at model time 0. And it is going to send, let's say, a randomly selected person a message. So we'll type, okay, sorry. So, okay, TAs to the front. In the palette, I opened up main in the palette, drag in an event, and then in the event properties, it should be, I call it initial infection. It's a timeout event. It occurs once at time 0. I didn't change those properties, just its name. And we're going to type an action here. And the action is going to be send a message to a randomly selected. And it's this dot deliver to random agent inside. This is what we'll do. And I'm going to deliver the infect message to a random agent inside of me. So let me go put that up there. You don't have to type it all out. You do this dot deliver, and you can choose random agent inside here. Okay? There we go. Indeed.
In doing that, you've got to remember exactly how you spelt that message earlier, haven't you? Because if you get anything wrong in that...
In general. And in a separate video, I show how you can do them without having to worry about that.
Okay.
Which, in this case, it doesn't matter because people are infected by any message right now.
Okay.
If we want it later to have multiple types of messages, you want to be very careful you're spelling them correctly. You don't want to leave it up to the vagaries of capitalization and so on.
Sure.
And you can use an option list. You can define an option list for all your messages.
Right.
And one option list will be infect with HIV, another, or exposure to HIV, another will be exposure to Hep C, another will be, exposure to flu. And you'll have those 3 messages, and then you would refer to that message from the option list. Does that make sense?
Yep.
Okay, folks, so should we run this thing? Who wants this more on the screen? Another minute for anyone? Okay, let's run this. Okay, this person is latently infected. What's happening, ladies and gentlemen?
So within the infective states, you had a transition. You commonly label those and
Oh, yeah, I would call it contact.
okay.
Contact transition, because it's not necessarily the infection immediately, because if they contact someone who's not susceptible, it won't actually transmit, right? So I'd call it contact.
And you generally show label then or show.
Yeah, I'd like to show the label. Sometimes you forget, but it's a good point. Yeah. Okay. Okay. So here we go. So do folks see this? Who needs help? Who needs help? Okay. Front there. Okay. Okay. So ladies and gentlemen, we have constructed our first model of interacting agents, transmission of infection through a network. Okay. So what I'd like to do now is to have a brief break, and we'll come back and we will continue on by introducing to this model a bit of statistics, and we'll show how we can show histograms about some common information, so additional output mechanisms. Okay? Question?
Now, in this question, since we had established a network,
Yes.
shown that some people had more network connections than others.
Yes.
When we start the infection, shouldn't that guide
So,
It should go in the direction where there's more connections.
yeah, except here the variability between specific individuals in terms of number of connections is pretty modest. People are, there are some denser connections for some reason, but they can't automatically jump to that area. And it can still, in terms of the sort of types of variability, more modest than you'll see in things like CL3 networks, where some people have tons of connections.
So that is happening.
It's right now it's spreading with such virulence that it's infecting everyone.
Oh, he's got the right condition.
And it's not specifically living only in the areas with large number of connections.
But you know, I mean, in a real situation,
Yeah.
and somebody going to school,
Yeah.
close on a lot of connections,
Right.
that would spread in that direction much more rapidly than it would to somebody, let's say, a farmer.
Indeed. The thing here is that
Going in
yeah, well, the issue is here that given exposed, if you're susceptible and you've been exposed to this bug here, you're going to get infected. It's a certain thing. The next thing we're going to do is we're going to introduce uncertainty there, and we will see that lends it means much more of a probabilistic sort of situation. Okay. Yeah.
Whoa!